All right, let's get started. So today I'm going to talk about optimal control and planning, and this will be the first in a series of lectures on model-based reinforcement learning. But first, let's start with a few logistical notes. So homework 2 is due today at midnight, and homework 3 is going to come out tonight also. For homework 2, I assume all of you that are in here have already finished it, and the reason the room is a little sparser is because those of you that are watching it online are probably watching it after midnight, having just finished the homework. That's okay. But homework 3, however, keep in mind, so this was going to be the homework on Q-learning. The training times there are going to be quite a bit longer because that's going to involve training convolutional neural networks to play Atari games. And if you're training those on CPU, it's going to take about 10 to 12 hours to really get the final result. So make sure that for homework 3, you start it early, because if you start on the day of, even if you do everything right, you might not have time to train your network. So start on that early, make sure you leave plenty of time for training. If you can run it on a GPU, you can actually get it down to like 3 hours or so if you have a good GPU. So start early on it. Okay, today's lecture. Oh wow, this is again messed up. Okay, so today I'm going to provide an introduction to model-based reinforcement learning. So in model-based reinforcement learning, unlike the model-free reinforcement learning algorithms that we've covered so far, we're going to look at what happens in the case where you either know the dynamics or you can learn the dynamics. So in today's lecture, we're going to just consider the case when the dynamics are known and talk about how you can make decisions under fully known dynamics. And then in later lectures, we'll talk about in the case where they're unknown, how you can actually learn them. We'll talk about some stochastic optimization methods, including a cross-entropy method. Then we'll cover a discrete search algorithm called Monte Carlo tree search that's quite popular in the deep RL literature. And then we'll talk about continuous trajectory optimization. So roughly in order, the stochastic optimization methods, these are applicable to a wide range of different problems, but they're not particularly scalable. MCTS is really intended for settings where you have discrete actions, and trajectory optimization is for continuous actions and smooth problems. So the goals for today will be to understand how we can perform planning with known dynamics models in discrete and continuous spaces. And then in later lectures, we'll talk about where we actually get those dynamics models in practice. So let's recap a little bit. Let's go back to the kind of reinforcement learning objective that we've been discussing so far in the course. So far, we've talked about this formulation where you have your policy pi. It interacts with the world. It produces actions. The world gives back states. The policy and the world together induce a trajectory distribution. And your goal is to optimize the expected reward under that trajectory distribution with respect to the parameters of the policy. And the policy might be either explicit, as in the case of actor-critic or policy gradient algorithms, or it might actually be implicit, as in the case of value function methods, where it's just recovered from the value function. So these are the settings that we've considered so far. And in all of the algorithms that we've discussed, the assumption is that this thing, the transition probability, the probability of going into a particular state given a state in action, is unknown, and furthermore, we don't even attempt to learn it. So all of the algorithms we've described, they don't assume that you know this thing, and furthermore, they don't even attempt to model this thing. They simply try to sidestep that issue by generating samples in the real world and using those samples in an appropriate way to acquire the policy directly without ever having to estimate these probabilities. So what if we actually knew the transition dynamics? What if we knew that P of st plus 1 given st at? Often in practical problems that we do want to solve, assuming that you know the dynamics is actually quite reasonable. So if you're playing a game, like you're building a machine to play Go, well, the rules of the game are actually very well known. So it's not unreasonable to say that you know the rules of the game. Some systems are easily modeled. So if you want to model a car navigating streets, just the high-level kind of kinematics of the car are actually fairly straightforward. The low-level dynamics might be very complex, but if you just want to model higher-level behavior, that's not too bad. Simulated environments, if you're trying to build a system that does something in simulation, whether it's playing a video game or controlling a simulated robot, well, if you're training in a simulation, then that means that you effectively know the dynamics because you have access to that simulator in your computer. For other systems, even if the dynamics are not actually perfectly known in advance, it might not be too bad to try to acquire them. So there's a large body of literature, for example, in robotics on something called system identification. So system identification means that you know something about the structure of your robot. You know maybe how many arms or legs it has, and you're trying to identify the unknown parameters, such as the masses or the friction coefficients of those parts. And of course, you can also use general purpose models. So you can actually learn the transition dynamics by directly fitting some sort of general purpose model, like a neural network or a Gaussian process or even linear regression, to data. So in situations where you don't know the dynamics, oftentimes you can attempt to learn them. So then the question is, does knowing the dynamics actually make things easier? So we discussed a number of model-free algorithms. If we have the dynamics model, can we do a better job of choosing actions? Can we in some ways make this easier, make it faster, make it more effective? Oftentimes the answer is yes, although it depends a lot on the specifics of the system in question. And we'll talk about some of the ways that we can make decisions with known dynamics today. So in general, model-based reinforcement learning has the following kind of high-level structure. In model-based reinforcement learning, we're going to try to learn the transition dynamics and then figure out how to choose actions under those learned transition dynamics. And in practice, this might be in the inner loop of some iterative algorithm that actually samples data from the world, and we'll talk about that next week. But today we'll talk about how we can make decisions if we already know the dynamics, so if somebody already did this first step for us. How we can choose actions under perfect knowledge of the system dynamics. Well, this is this part, so if you remember this Bayesian network that I drew in the second lecture, we have states, actions, observations, and I'm using slightly different notation here, but hopefully all of you can figure that out. And the transition dynamics are this thing. It's what gives us the probability of the next state given the current state in action. This is the problem solved by optimal control, trajectory optimization, discrete planning. They're all basically solving some variant of this problem, given known dynamics, figure out how to choose the actions. And then next week we'll talk about the unknown dynamics, and then after that we'll talk about how we can learn policies, how we can learn this thing. But for today, let's just say that we have this, our system, our states, and our actions, and we'll just ignore the policy for now, and we'll just worry about choosing the actions directly. So we'll come back to policies later. For now, we'll remove the policy and just worry about how you can choose these actions to get the reward you want. And what you want is maybe there's some kind of goal you want to achieve in the tiger thing that I discussed before. Maybe you want to minimize your probability of getting eaten by a tiger, which in general corresponds to some cost or reward. So in a deterministic environment, we can write out the thing that we're after by saying we have some cost or reward. We either minimize the cost or maximize the reward over states and actions. We're going to choose the actions. And we have some constraint that says the next state is given by some function of our state in action, which for now we'll assume this function is known. So that's the deterministic case, and we can schematically draw it like this. You have your learner, you have your machine, and you have the world. The world tells the machine, you're going to start in this state, and then the machine is going to think about it. It's going to use its model of the world and think of a sequence of actions that it can take to achieve the thing that it wants, and then it hands back that sequence of actions to the world and says, OK, here's my plan. Let's execute it, and let's see what happens. So the corresponding optimization problem can be written out like this. On the previous slide, I had a cost. Here I have a reward, but it's the same thing. Maximize the reward such that your transitions follow this, the dynamics. So this is deterministic, and it's open loop control. And I'll talk about what open loop and closed loop means in a second. Now, you can also have a stochastic version of this stuff. You can say, OK, here your transition dynamics are deterministic. What if they're stochastic? So you can formulate a stochastic open loop problem as following. You can say the world gives you a state. You think about the world. You construct a conditional distribution over the states that you'll see given some actions. So here the policy is no longer in here because this is all conditioned on a plan. It's conditioned on a sequence of actions. So I don't need the policy inside this big product. But the objective is the same. I'm maximizing the expected reward. It's just that now it's conditioned on a sequence of actions. Here's a question. In this setup, in the stochastic open loop case, why might it be a bad idea to solve the problem like this, to solve for a sequence of actions that maximizes the total reward conditioned on that sequence of actions? What might be a problem with this setup? Yes?
Multimodal or high variance.
So you might have multimodal or high variance dynamics, but what in particular about the sequence of actions might cause problems in that case? So imagine that, let's say, there's some stochastic dynamics in the world. Maybe I'm trying to navigate this building, and I don't know exactly how this building is laid out. So I'm going to walk out into the hallway, and I'm going to look around to see if I see an exit sign. I'd like to exit the building. When I'm standing here in this room, maybe I don't know where the exit is. I don't know if it's going to be on the left or on the right. So I'm going to stand here, and I'm going to think, well, I'm going to exit. and go left, let's say, arbitrarily, right? But as soon as I leave the door, I can look around and I can see where the exit is. And at that point, I can actually change my mind. So in an environment with stochastic dynamics, if I commit to a sequence of actions in advance, that's going to give me a suboptimal solution, because when I actually take the first action, the stochasticity of the environment will resolve itself, and I'll actually see the second state. And at that point, once I see that second state, I can make a better decision about my second action. So this is why this is called the stochastic open loop case, because you can also have a stochastic closed loop control, which is going to address this problem. So in general, in a stochastic environment, committing to a plan like this can be suboptimal, and we can do a little bit better. But there's just a little bit of stochasticity. This can often be OK. There's a question?
Yeah, I had a question about notation in the previous slide.
Mm-hmm.
You said that AT plus 1 is a function of ST and AT.
Mm-hmm.
That's because ST and AT fully determine ST plus 1.
Yep.
And then the action that you take at ST plus 1 is also deterministic?
Well, so in this case, the action that you take it's just a plan. So there's no policy here. You're just optimizing over a sequence of actions. So they're deterministic in the sense that they're variables you're optimizing over. So here there's no policy. You're just constructing a plan, a step-by-step plan of I'm going to do X, then I'm going to do Y, then I'm going to do Z. OK, so this is the stochastic open loop case. And just a little aside on terminology. What is this loop? Probably a term that you've heard before. When someone says closed loop, what they really mean is that the environment produces a state, the machine looks at that state, produces an action, typically according to some policy, and they go around and around. So every time there's a time step, the environment produces a new state, and the machine gets to choose a new action according to its policy. So it's a closed loop in the sense that there's a closed loop between the machine and the world. Open loop refers to this picture, where the environment tells you, you're going to be in some state, and then you come up with a behavior, and you sort of commit to that behavior, and then you execute it blindly regardless of what happens next. So typically when someone says open loop or closed loop, they mean, are you continuously reacting to your states or observations, or are you committing to a plan and then carrying out that plan? So in the open loop case, it's sort of a one-way relationship, really, because even though we get to see the first state, we don't get to really pay attention to anything after that. So in the stochastic closed loop case, this is the more familiar setup that we saw before. We do have a policy, and we maximize the expected reward with respect to that policy. Now, you can actually do planning over very simple policy classes. So far we've talked about very complex policy classes like neural nets. Later on in today's lecture, we'll actually talk about a very simple policy class that you can optimize using trajectory optimization algorithms. So we talked about neural nets, which is a very kind of global policy. It gives you a distribution over actions in all states everywhere in the world. Later on, we'll talk about these very simple time-varying linear policies that it's basically like a plan with a little bit of feedback, essentially. So a time-varying linear policy tells you, OK, take this action KT, but correct with a little linear feedback. And this is a very local class of policies. This is the kind of stuff that comes up in optimal control a bit. So we'll talk about that more, too. Main point here is to keep in mind that just because there's a policy pi doesn't mean that it's something really complicated like a neural net. It might be something very simple and local. OK, so the first type of planning algorithm we'll discuss is a very simple type of planning algorithm that we can use if we have relatively small kind of short horizon problems, which is stochastic optimization. And I already alluded to this a little bit when I talked about doing Q-learning with continuous actions. So if you remember, I talked about this randomly sampling actions and then taking the best one. So stochastic optimization methods are basically fancier versions of the same idea. So what we can do is we can take our optimal controller planning problem and we can abstract it away a little bit. We can say that, well, what we want to do is we want to choose a sequence of actions that maximizes something, some functions of that sequence of states and actions. And maybe that function is going to involve rewards and dynamics, but for the purpose of this method, we actually don't care what it is. It's just some function of a sequence of actions. So we don't care what it is, and we just want to maximize it. And we'll just write it out like this for simplicity. We'll say this. We have this capital A, which is an entire sequence of actions. So the simplest method to do this maximization, if you don't want to worry about computing derivatives or anything like that, and if A is sufficiently low dimensional, is to do guess and check. This is what we discussed on Monday. Pick some sequence of pick some set of action sequences from some distribution. For example, just sample them uniformly at random, evaluate all of their returns, all of their J's, and then pick the best one. Very simple method. Works well if you have very low dimensional A's, but doesn't scale very well. So this is sometimes referred to as a random shooting method, which is an overly descriptive way of basically describing guess and check. But there's a variant on this method that does tend to work a bit better and actually provides a fairly decent optimization technique for sort of medium to low double-digit number of dimensions, so like 30 to 50 dimensions, which is called cross-entropy method. So if we go back to this guess and check approach, I said that we're going to pick some sequence of A's from some distribution and then choose the best one. And then the question is, which distribution do we use? So we could just sample all legal A's. So if we have, let's say, bounds on our actions, we just sample everything within those bounds uniformly. But we can do a little bit better. So here's what we could do. We could say initially, let's just sample uniformly. And we sample some action sequences uniformly, and we see that these two over here are a little bit better than the rest. And then what we can do is we can actually adapt our distribution. We can say, these two guys are looking a little bit better, so let's fit a little distribution just to the best ones and resample from that distribution. So let's generate more samples in the region that looks most promising right now. And then we can take that, those additional samples, the green samples, fit another distribution to them that's going to be a little more concentrated at the optimum, and then resample from that. And this is a very simple modification to the guess and check approach from before that tends to work substantially better. So here's how we can write out this algorithm. Step one, we sample our action sequences from some distribution P of A. Maybe initially it's just a uniform distribution. Step two, we evaluate the value, the return of all of these sequences. Step three, we pick what's called the elites, so a subset of all these A's that have the highest value. Maybe we pick, let's say, the 90th percentile or the 80th percentile. And so we choose a subset of them where we choose M of them where M is less than N. And then in step four, we refit our distribution to just the elites. So that's where we had these 4 yellow samples, and we fit the Gaussian to just the 2 best yellow samples. Yes, there's a question.
But if the original function j of a has a very narrow, large peak, this is almost always guaranteed to miss it.
Of course, yeah. So if your function is ill-behaved, where there's, let's say, a big Dirac delta in the extreme case and a big plane everywhere else, then this method won't find it. Yeah. And it can be exponentially bad under certain pathological conditions. So this is basically the cross-entropy method. Oftentimes, for the distribution that you're fitting, if you're using continuous actions, you might choose a multivariate normal distribution. If you have higher dimensions, maybe you choose a multivariate normal with a diagonal covariance so that you don't have to build a big n by n matrix. And another thing that you might want to check out if you're interested in a method like this is something called CMAES, covariance matrix adaptation, which is essentially an improvement on cross-entropy method that introduces something that looks a little bit like momentum, where you don't just refit the Gaussian just to the elites each time step, you sort of keep track of the direction in which your Gaussian is moving. So this kind of approach is it's not actually like a really good optimization method. It's just really simple. And if you're doing this with, let's say, neural network dynamics models, it can be very efficient because all this sampling here can be done, and all this evaluation can be done in parallel across all the different A's. Yes?
Sorry, I have another question. Why is the Gaussian actually preferred here? Wouldn't it be better to have something like Lorentz, something that decays power law in the tail?
I can see that, yeah. I'm not aware too much of the analysis on using different distributions. I have a strong suspicion that a big part of why Gaussians are very popular is just because of the simplicity. So typically, if you're going to design a better optimization algorithm, there's many things you can do that are much better than this. But if you need something that's computationally efficient that you can code up in 15 minutes, this is often a good choice. So yes?
But doesn't Gaussian assume there's only one mean? So if there's like 2 peaks on 2
Yeah, so this is a very good question. In general, you're going to have exactly this problem. So if you have, let's say, a good sample here and a good sample here, you'll fit a Gaussian that covers the middle. After a while, you will actually have a tie-breaking effect. So you can actually show that if you do run this thing for enough iterations, it will actually pick out one of the 2 modes. And if you generate enough samples, in the limit of infinite samples, it'll basically pick out the right mode. And that's just because you do this decimation each step, so you always pick the elites. That said, if you have a highly multimodal function and use too broad of an initial distribution, you can have this problem where for a small number of iterations, it will actually average them out. In practice, I found from my experience, this is often not as huge of a problem as it seems. Yeah. Any other questions about cross-entropy method? OK. So don't want to dwell on this too much, because like I said, not the best optimization method in the world, but something that's really simple and kind of good to keep in your toolbox if you need to set something up very quickly. So the upside, it's very fast if it's parallelized and extremely simple. The problem, it has a pretty harsh dimensionality limit. So this sort of sampling-based approach, it's not even the pathological cases like the Dirac delta on an infinitely large plane. Even more reasonable functions in higher dimensions will cause this thing a lot of problems, just because you can very easily miss the good regions. And it's only providing you with open loop planning. So there's no notion of accounting for the fact that you'll take an action, observe something, and then be able to better choose your next action based on what you observe. So this is only doing open loop. All right. For the next method that we'll discuss, this one is actually doing something that looks a little bit like closed loop planning and a more sophisticated search procedure that's going to scale better to more complex problems, and that's Monte Carlo tree search. So Monte Carlo tree search, very popular choice actually for, especially for discrete action problems. So I'm going to use as my illustration this little Atari game where you have to control a little submarine, and you have a discrete set of actions that indicates which way you move the submarine, and also whether or not you push the button to fire the torpedo. So for some reason in this game, you're supposed to blow up the fish and pick up the divers. Anyway, so you can formulate the task of playing this game, which in this case is actually deterministic, but it could be stochastic too, as a search problem, as a tree search problem, where you say that, OK, you're going to start off in some state. You're going to expand the nodes that correspond to all the possible actions from that state. And if you have known dynamics, you'll actually ask your dynamics model to tell you what will be the state if I take this action, what will be the state if I take this action. The subscript here denotes the time step, by the way. So they're both S2 because they're both at the second time step. Then you go there, and then from each one, you expand every possible action thereafter, and so on and so on. Now, just doing this sort of exhaustive search that I described, of course, is a very bad idea because it's going to scale exponentially with time. So what can we do? Well, what we can do is we can say, let's search to some depth, and then after a while, once we get a little bit into the future, let's heuristically evaluate the value of that state instead of exhaustively enumerating all possible actions. So in particular, if we have some kind of policy, even if it's not a really good policy, we can just reach down to the leaves of this tree, and at the leaf, run our policy. And running the policy now, this is not exponential. This is just, this cost is going to be the length of this run times the number of leaves. And we're going to run that policy, and we're going to use that to estimate roughly the value at each of the leaves. And the further down we expand this tree, the less demand there is on us to have this policy be really, really good. So the intuition is that if you took some actions that put you in a situation where you've basically already won the game, at that point, even a really lousy policy like a random policy should be able to basically finish the job for you and tell you if you've really won. And if you put yourself in such a terrible situation that you'll definitely lose the game, you might as well just run the random policy and get to that final score that actually tells you that you've lost. So for that reason, oftentimes when people do Monte Carlo tree search, the actual policy that they use to evaluate the leaves is actually just a random policy. And the further down you go in the tree, the less important it is to choose that policy very well. Now, the trouble is that even for a moderate depth, this thing is still exponential, so you have to be a little bit picky about which leaves you search. So you can't search all the paths. Where should you search first? Well, the intuition in Monte Carlo tree search is to search the most promising leaves with a little correction to also search leaves that you haven't visited very much before. So for example, you might take this action, action 0 in state 1, run your policy and say, OK, this policy came up with a total reward of plus 10. And then you expand this other leaf and you say, oh, this one came up with a reward of plus 15. Now, you don't know that this 10 and 15 is actually the value of those leaves, because this is some lousy policy. And beyond that, the system might even be stochastic. So if you take this action 0 twice, you might actually end up in a different state. So you don't know for sure that this 10 and 15 is actually the value of those leaves, but based on the information you have, it's sort of reasonable to surmise that this state might be a little bit more promising than the other one. So if you have a finite amount of resources and you have to commit them to one state or the other, maybe it's better at the moment to spend a little bit more time exploring this more promising state. So the intuition is to choose the nodes with the best reward, but also prefer the nodes that you haven't visited very much. Because there's all this stochasticity due to this policy being random and due to this transition being random, that you might want to, if you've undersampled some leaf, visit it again. Yes?
Does the reward on the leaf include the reward that was accumulated, like getting to it at this point?
We'll see that in a second, but the way I'm writing it now, I just mean this piece.
Okay.
But the way this works will be obvious on the next slide. OK, so to sketch out the full MCTS algorithm, let me write it out and then sort of walk you through an example execution of this method. So the way that Monte Carlo tree search works is step 1, for the leaf that you're currently in, find its child leaf using something called a tree policy. And I'll explain what the tree policy is in a second. Step 2, evaluate that leaf using the default policy. This is that random thing. It doesn't have to be random, but oftentimes a random policy is used. And then step 3 is update all the values in the tree between the node that you just evaluated and the root. And then you repeat. And then you just take the best action from the root. And then typically you'd repeat the whole process. So I'll explain the tree policy in a second, but the intuition behind the tree policy is just pick the child that has the best value with a little correction that also says visit children that haven't been visited recently, even if they have slightly worse value. So when you start off, you're going to evaluate an action arbitrarily because you have no way of choosing one or the other. And then once you evaluate that action, you get the second state. And now you're going to step 2, evaluate the leaf using default policy, run your random policy, and you get a value. And what you store at this leaf is the total rewards that you've gotten and the number of times you've explored it. So I got a reward of 10, so I'm going to store q equals 10. And I visited it once, so I'm going to store n equals 1. And now I'm going to visit the other child. Until the root is fully expanded, I'm going to visit all of its children in order. So I haven't visited the other child. I'll go visit that, run the random policy, and I get, let's say, q equals 12 and n equals 1. Now I have to choose. Now I have these 2 possible nodes, and I get to choose one of them. And this is where the tree policy matters. So a very reasonable tree policy, there are a few different choices for this, but I'll outline one popular choice. If a node is not fully expanded, choose actions arbitrarily. So that's why I chose these 2. Otherwise, if the node is fully expanded, then choose the child with the best score. And the score is, if the children have equal visitation probability, you just take the one with the highest number. So that's what we're going to do here. We'll go and expand this one. And maybe here we got a 10. We visited this node once. But now we visited this node twice. And we add together the values. So there was a 12 here before. We got a 10 now. So the total is 22 now. OK, so we visited this node twice now. And now we have to choose. And here the score really matters. So one example of a fairly popular score is the average reward at that leaf, so q divided by n, plus a little term that says how often have you visited that child from that parent. So here, this natural log n is st minus 1. This is the number of times you visited the parent divided by the number of times you visited the child. So here, if you visited the parent a huge number of times and you visited the child very rarely, then you'd prefer to choose that child. If you visited the parent many times, but you've also visited that child many times, then you might prefer to choose a different child. So based on this rule, when we look at this tree as it is now, we might say, well, even though this one averages an 11 and this one averages a 10, this one has been visited twice and this one's been visited only once, maybe we prefer to visit this one because we haven't been there as often, and the difference in score is not that large. So now we'd expand the left child, choose an arbitrary action, and maybe this one gets us a q of 12. And now, again, we go back up the tree and update all of them, so this one becomes a 2 with a 22. So now there's a tie at the top. We choose one of them arbitrarily. And maybe we go left again. We get an 8. This one is a 1, this one is a 1, and this one's not going to be a 3. And its average is a 10. So now this one looks clearly better. It's been visited less, and it has a better average score. So we're going to go right and expand its other child. And then we keep going like this until we run out of time. So if we have some kind of budget for planning, we go for a fixed period of time, and then we commit to the action that currently has the best estimated value. Does anyone have any questions about this? Yes?
What do you mean by the state is fully expanded?
Meaning all of the actions have been taken.
So we assume we have finite action.
Yeah. You can generalize this algorithm to continuous actions also, and then there's a slight modification where you would actually deal with the case where some child has been expanded 0 times. You can't use this score because if you plug a 0 in here, you get infinity. But there are other variants that can handle that. OK. So this is Monte Carlo tree search. And a few additional readings if you want to learn more about Monte Carlo tree search. This is a survey of MCTS methods with a kind of a nice basic summary. And it also outlines a few different options for score functions and the tree policy. And here is an example paper that used a combination of Monte Carlo tree search and actually supervised learning to learn to play Atari games. So this is by Xiaoxia Guo from University of Michigan. And what they did in this paper is they actually had a Monte Carlo tree search planner playing Atari games. And they used this Monte Carlo tree search planner to train a policy, actually using Dagger. So when we talked about Dagger, if you remember in the imitation learning lecture, we discussed how you train your policy using data, you run your policy to see which states it visits, and then you ask a human to label the actions from those states. In this work, there's no human anymore, there's Monte Carlo tree search. So in step 3, you instead choose the actions in the states visited by the policy using Monte Carlo tree search. So you actually run Monte Carlo tree search, or you run the current policy, you see which states it visits, and from each of those states, you run Monte Carlo tree search to figure out which action it should have taken. And then you relabel those observations with that action. So this is an example of using Monte Carlo tree search and also an example of imitating an optimal planner, which we'll talk about more next week also. So one reasonable question that might come up here as well, if you're going to use Monte Carlo tree search to actually play the game, why do you need to then train a separate policy, in this case a convolutional neural network? Well, in this case, for this paper, their issue was that MCTS is actually too slow to actually play the game in real time. So if you want to be able to play the game quickly, you can get a lot of benefit from actually training a network to approximate the behavior of MCTS. But there are other reasons why you might want to sort of distill a planning algorithm down into a policy, and we'll discuss those more later as well. Things like dealing with perception, generalization to new states, and so on. OK. So at this point, we'll take a 3-minute break, and after we come back, we'll talk about trajectory optimization. OK.
So I was wondering if it would be possible for me to complete the homework.
Yeah, so for everybody who got an enrollment code just now, the email that sent you that code should have said that there's a different date if you just enrolled for the homework.
OK. I just got a regular email from the lecture.
OK. You can talk to me after the lecture, and we can discuss it.
Thank you.
Okay, let's continue. So before the break, I talked about stochastic optimization and also about Monte Carlo tree search, which we can use for planning, especially with discrete actions. Now I'll talk about what we can do for continuous control problems. And I'm going to change up the notation on you a little bit here, which this kind of notation is a bit more common when dealing with optimal control and trajectory optimization problems. So if you want to sort of, if you want to get the mental translation here, X is state now, U is action, and we have costs. And if you read papers on trajectory optimization, DDP, and LQR, you'll typically see this notation. So I'd like to use it here just so that you can make that connection. So the kind of problems that we'll deal with in the second half of this lecture are ones where both states and actions are continuous. And we're going to look at introducing derivatives into the mix. So this is the problem that you saw before. This is minimizing your cost subject to some known dynamics. And what we can do here is, because the constraint is an equality constraint, we can actually substitute inside the objective and rewrite an equivalent unconstrained problem. So we can say, OK, x2 is just f of x1, u1, so we'll just substitute that in there, x3, and so on until we get to the end where you have f of f of f of f, and so on. People don't typically write it like this because, for reasons that should be obvious from seeing this written, it's a huge pain to write. But it's a lot more convenient to actually do things this way because now it's unconstrained. So we've just substituted the x's, and now we just have an optimization over just the u's without any constraints. Now this is very convenient because at this point, if you have an unconstrained optimization, you can imagine using differentiation via backpropagation and your favorite gradient descent style algorithm to minimize this. So if you want to do backpropagation, just like we do with neural nets, the thing that we need is derivatives. And specifically, the derivatives that we need are the derivatives of f with respect to x, the derivative of f with respect to u, the derivative of the cost with respect to x, and the derivative of the cost with respect to u. So if we have these derivatives, then we just apply the chain rule gratuitously over all the time steps, and we can compute the derivative of the full objective with respect to each of the actions. Now in practice, this is often not a very good idea. And it actually really, really helps to use a second-order method rather than first-order gradient descent. And the reason for this is that this first action, u1, it's going to appear in many, many of these places. So the sensitivity of the overall objective to u1 is enormous. So if you imagine that, let's say, your actions are, maybe you're flying a rocket or something, and the actions are how you're going to throttle the engine of that rocket. If you're flying the rocket in space, then momentum is conserved. So as soon as you apply a little bit of thrust, it's going to affect your position a long period of time into the future enormously. Whereas that very last action that you apply is going to have minimal effect on your final position. So the very first action has a huge effect. The second action has a huge but slightly lower effect, and so on and so on. And in practice, this very high sensitivity means that the gradients are going to be pretty ill-conditioned. So this is sort of going to be the world's worst exploding or vanishing gradients problem. And that makes using standard gradient descent methods for trajectory optimization actually extremely difficult. But the particular structure of this problem, the fact that you have all these costs that are summed up over time, makes it actually very convenient to derive very efficient second-order methods. And that's actually what we're going to talk about today. So this is not actually directly related to training any kind of neural nets for anything, but it's a tool that's going to be quite useful for a lot of reinforcement learning style problems. So we're going to talk about second-order trajectory optimization. Before I do that, a little bit of terminology. One of the things that you might hear when you hear about trajectory optimization algorithms is you might hear the term shooting method or collocation method. So shooting method refers to algorithms that optimize over the actions and consider the states to just be outcomes of applying those actions. So that's basically what we're doing when we fold the constraint inside the objective and write an unconstrained problem. And the reason it's referred to as a shooting method is because that action that you apply in the earlier stages sort of affects wiggles around the end of that trajectory by some very large amount. So it's as though you're shooting out this trajectory and seeing where it is that it's going to land. Collocation methods maintain the constraint, and they actually optimize over both states and actions, or sometimes even over just the states, with the actions actually being a consequence of the states. So the intuition behind collocation methods is that you drop a bunch of these pins into the world, which are the states, and you're going to move the pins around, which is going to be quite a bit more well-behaved, but you still then you have this constraint to deal with. So if you're willing to solve a constraint optimization problem, you can do a collocation method, which is going to be a bit more stable. But if you want to do an unconstrained thing, then you have to deal with this problem. So we're going to actually do this using a second-order method today. So before we derive an optimization algorithm for nonlinear dynamics, we'll actually go through a simpler case of linear dynamics, at which point you can do something called LQR. LQR stands for linear quadratic regulator, and it's a method for obtaining actually both an optimal trajectory and an optimal controller in the case where we have linear dynamics and quadratic costs. So we'll start with that, and then we'll see how we can actually generalize this to the nonlinear case, which is much more useful for the kind of systems that we'll see in practice. So let's go back to our unconstrained optimization problem. And when we say linear dynamics and quadratic costs, what we mean is literally this, that f is given by some matrix times x and u plus some vector. So this is sort of the constant part, and this is the linear part. This is a pretty limiting class of dynamical systems, but it's very, very convenient to deal with. And the cost is quadratic, which means that it's some matrix that you hit on either side with x and u, and some vector that multiplies xu. So this is the quadratic term, and this is the linear term. There is also, in general, a constant term, but for the purpose of the optimization, we actually don't care about the constant term. OK, so this is the setup that we're going to work with, and then we'll see how the solution to this can actually also get us a solution for the nonlinear case. So linear dynamics, quadratic costs. Now, in the next few slides, you'll see a whole lot of linear algebra. So don't get too concerned about that, because in the end, actually, it ends up reducing to a fairly simple algorithm. But there will be a lot of letters on the screen. So that's how that fits in there. And now we have this system, this cost, and this dynamics. And what we'll do is we'll actually start in the back. We'll start by finding the optimal last action, and then we'll go backwards. And the reason we do that is because the last action only influences the last cost. So it's very easy for us to just find the last action. Yes?
Do you mind going over the notation again? What's x and u and f and c?
X is the state, u is the action, f is the dynamics, and c is the cost. OK, so since this is the only term that depends on the last action, it's awfully convenient for us to start by optimizing just the last action, because this we can actually do very easily. The trouble is that the last state is unknown. So we can't actually find the last action numerically, but what we can do is we can express the last action as a function of the last state, the optimal last action. So this is our cost, and I've written it with a q in front for reasons that will become apparent on the next slide. But if you imagine q functions, since we're doing cost instead of rewards, q functions now are actually cost to go rather than reward to go, but same deal. At the very last time step, since there's no next step, the q function is exactly equal to the cost. So I can write out my q function just by putting in the cost function. And now I'm just going to take this equation, and I'm going to minimize it with respect to u, because I'm trying to minimize the cost. U only influences the last step, so I'm allowed to do that. It's quadratic, so minimizing with respect to u is actually fairly easy. All I have to do is I have to compute its derivative with respect to u. Derivative of quadratic, very straightforward. This term just becomes, well, I should explain the notation here. So when I have this matrix C, I'm breaking it up into 4 parts. The top left part is the part that multiplies the x's. So you can see here the x is on top. So the top left part is the one that's going to multiply the x's. The bottom right part is going to multiply the u's. And the top right and the bottom left are going to be u transpose cux x terms. So they're the cross terms. So the reason I'm breaking it up like that is because I'm going to want the derivative with respect to u, not with respect to x and u. So now I have to pull apart this matrix in order to write out that derivative. So in that derivative, I have the derivatives of the cross terms, which end up looking like this. I have the derivative of the term that's quadratic in u that looks like this. And then I have the part that multiplies the u here for this vector. So the vector is broken up in the same way. So all I've done here is I've substituted this in for the matrix and vector and written out its derivative with respect to u. And now if I want to optimize it with respect to u, all I do is I set the derivative equal to 0, and I solve. So this is just the kind of stuff that we all learn in calculus. We just crunch the numbers and solve for the u. Now, this requires us to do a matrix inversion, because we take all these constant terms, this one and this one, we push them over to the right side, and then we hit it by CUU inverse on both sides. So that means that the optimal u is given by the negative CUU inverse times CUXX plus lowercase c. So I've just put the constants on the right and inverted CUU. Now I have an expression for the optimal final action. The trouble is that this expression is expressed in terms of the last x, which I do not know yet. it's worth noting that this expression can be viewed as a kind of policy for the last action. So a deterministic policy is just a function of the state, and this is a function of the state. And I can write it out like this, capital K times x plus lowercase k, because this is shorter, where capital K is given by this matrix, and lowercase k is given by this vector. So all I've done is I've just combined these terms into big K and combined this matrix inversion and this vector into lowercase k. So now, I haven't solved for the last action, but I have solved for a controller, a policy, that gives me the last action as a function of the last state. And that's going to be very convenient. And now what I can do is I can basically substitute. So I have this equation for my Q function, and I have this equation for my U, and I basically can plug this in for U, and I'll get my last Q function expressed entirely in terms of x with the last U completely eliminated. So since U is fully determined by x, we can eliminate it via substitution. So we'll substitute it. And then this I'm going to call a value function, right? Because that's what a value function is. A value function is a thing that optimizes the Q function. I've optimized the Q function. I plug in the action, and I get a value function. So now I have a value function for the last time step. Now I'm going to write out a big, scary equation. But don't be worried about this big, scary equation, because this thing, all I've done is I've taken this and I've expanded out the C matrix in the lowercase c with the CXX and the CUX and so on. And it's a giant horrible alphabet soup. But the really nice thing about this horrible alphabet soup is that everything in here is either linear or quadratic in x. So even though there's a lot of terms, they all can be grouped into two categories, terms that are quadratic in x and terms that are linear in x. So all I have to do is I have to collect all the quadratic terms, collect all the linear terms, and put the constant terms in the garbage. And then I get an equation for v of x that looks very clean, very simple. And if you want to know what those capital V and lowercase v is, this is what they are. And you can just copy it down and type that in Python and get everything working. So horrible alphabet soup, but actually very simple conceptually. So now we have a value function. And the value function is just a quadratic term in x and a linear term in x. So now, let's go one step backwards. Let's solve for the optimal action at the second to last time step. Just like before, we can't get a number for the second to last action, but we can express it as a function of the second to last state. The only additional challenge is that the second to last action is going to affect the last state. But we know how it's going to affect the last state. It's going to affect it through the dynamics. So we know that x capital T is equal to ft minus 1 times this vector that stacks a state in action plus the constant term in the dynamics. So that means that the Q function at time step t minus 1 is the cost function at step t minus 1 plus the value function at time step t, the value function at what state? At the state that you get if you take that action in that state, right? And we know f and we know v. So this is our v, and we plug in the f. So if we replace the x capital T in here with this expression for x capital T, we plug it in. Again, we get a horrible alphabet soup. But just like before, in this horrible alphabet soup, everything is either linear or quadratic. So even though it's a big wall of math, it just consists of terms that are linear or quadratic in xt minus 1 and ut minus 1. And all we have to do is rearrange them and pull out the linear and quadratic terms. So in particular, these are the quadratic terms, these are the linear terms, and we can just collect all those and stuff them into a big matrix and a big vector. So there's our Q function, there's our value function, and we collect all the quadratic and linear terms, and we can write out our Q function at time step t minus 1 as some matrix capital Q that hits xt minus 1 and ut minus 1 on either side, and some vector times xt minus 1 and ut minus 1. And the way that we get that matrix and vector is just by collecting all the quadratic terms and all the linear terms from the cost and from this expression for the value of the next state. And these are the equations for the matrix and vector component, in case you're curious. And now we do exactly the same thing. So the optimal action is the one that minimizes the Q function. So we just take this expression for the Q function, we compute its derivative with respect to u, and we set that derivative to 0. And this expression is exactly the same as the one that we had at the last time step. I've just replaced all the c's with q's, right? Because before it was quadratic with capital C and lowercase c. Now it's quadratic with capital Q and lowercase q. But the math is exactly the same. I set it to 0. I solve, meaning I push all the constant terms to the right, and then hit it on both sides with QU inverse. and I get ut minus 1 is equal to some capital K xt minus 1 and some lowercase k. And the uppercase k is given by this. Again, exactly the same as before, except that now they're q's instead of c's, and the lowercase k is given by this. So a whole bunch of math, a whole bunch of linear algebra, but conceptually exactly the same as the last time step. And then we just proceed like this. So we go to step t minus 2, and again repeat the same operation because we can compute the value function and so on. So the algorithm for actually solving for capital K and lowercase k at every time step can be written as a backward recursion. So we start at the last time step, and then we proceed backwards in time until we get to time step 1. And at every time step, we compute our uppercase q and lowercase q by taking the cost plus the next value. We get our quadratic q function. We figure out the u that minimizes that quadratic q function to get capital K and lowercase k. We plug those in to evaluate the value function, the uppercase v and the lowercase v, and we get the value function. And now we're ready to start over again. So once we've got that value function, we have everything that we need for the preceding time step. And we just keep going like this until we get to time step 1. So this procedure will give us a linear feedback controller at every single time step, starting at the end of the trajectory, going all the way back to the beginning. And once we get to the beginning, we're in luck because we actually know the first state. That's the only state that we do know. So once we know the first state, we can basically go back forward, essentially unzip this whole thing and get an action, an actual numerical action for every single time step. And that we can do using a forward recursion. So once we've computed all these k's, we've now expressed the action at every single time step as a linear function of the state at that time step. And we have the state at the first time step. That means we can compute an action at the first time step. So for every time step from 1 to t, we compute the action using the k's that we've computed. And then we can compute the next state because we know the dynamics. So then we take xt plus 1 is the function of the now known xt and ut. Then we plug in xt plus 1 into the next time step, get an action on the next time step, and repeat. So we go backwards, compute all of our k's, and then go forward and compute the actual numerical u's. And now we have a set of u's that will actually minimize our quadratic cost. And this algorithm is exact. So if you have linear dynamics and quadratic costs, this will allow you to exactly compute the actions that minimize the cost over all time. OK. Does anybody have any questions about LQR? OK. A few useful definitions. This is, I think you guys should already heard this in previous lectures, but the Q function, this is the total cost from now until the end if we take u in x. So this is a Q function just like the Q function we had before. And the value function here is a value function just like in the model-free RL case. It's the function of the state that gives you the Q value for the best action. So same exact formulas as before. The only difference is the sign. Before we had rewards, now we have costs. So the values and the Qs are actually the cost to go, not the reward to go. Now, one question that might come up is, well, can we use this approach if we have stochastic dynamics? So far, at deterministic Fs. If you have stochastic dynamics, in some cases, you can actually use this method and actually get the right answer. So if we have deterministic dynamics that are just matrix times vector, one thing we can do is we can say, OK, let's also model stochastic dynamics that are matrix plus vector with some noise. So in the special case where we have stochastic dynamics that are Gaussian, meaning the F is the mean, and then there's some Gaussian noise that corrupts the next state. In this particular special case, we can actually express the optimal solution also using LQR. And this is actually like a fairly common way to model stochastic systems if you basically assume that they're basically deterministic, but then corrupted with some unimodal Gaussian noise. So in this case, you can actually still choose your actions according to exactly the same feedback control law. And there's actually no change to the algorithm. So you can actually ignore the noise. And the reason for this is that essentially the different outcomes under the Gaussian are symmetric. So you can check this as an exercise if you'd like, because the expectation of a quadratic under a Gaussian actually has an analytic solution. So you'll get these additional terms in your cost that look like sigma times the quadratic part of the cost. But it turns out that if you actually crunch the math and figure out the optimal u, there's actually absolutely no change in it. So in the case where you have Gaussian dynamics, where the mean is given by f, and there's some constant covariance. It can be different at every time step, but it can't depend on the state. It turns out that the optimal solution is to just use exactly the same algorithm and ignore the noise. If your noise does depend on the state or the action, then things get a lot more complicated. OK. Now let's deal with the nonlinear case. So far we discussed how we can solve for the optimal actions if you have linear dynamics and quadratic costs. Now that's a very specific and somewhat peculiar set of assumptions. There are real-world systems that satisfy those assumptions, but we would really like to be able to handle any real-world system that we can differentiate. So in that case, we have to make an approximation. So in the nonlinear case, I'm going to actually derive an algorithm called iterative LQR, which is very similar to something called differential dynamic programming, and I'll explain the difference at the end. So let's talk about iterative LQR. The idea in iterative LQR is that we know how to solve for the optimal trajectory if we have linear dynamics and quadratic costs. So if we have a nonlinear system, we're going to locally approximate it with a linear quadratic system. And the way that we locally approximate it with a linear quadratic system is that we take our nonlinear dynamics and we do a first-order Taylor expansion, and we take our nonlinear cost and we do a second-order Taylor expansion. So when we do the first-order Taylor expansion, the linear part of the dynamics simply becomes the derivative of f with respect to x and u. And when we do the second-order Taylor expansion, the quadratic part of the cost is the second derivative, and the linear part is the first derivative. So you have to perform this Taylor expansion around some trajectory. And when I put together the whole algorithm, you'll see where that trajectory comes from. So if we have some trajectory to begin with, we have some sequence of x hats and u hats, you can perform this Taylor expansion. And when you perform this Taylor expansion, now you simply say that we'll have dynamics f that are on these delta x's and delta u's. So in the Taylor expansion, now it's this grad f times x minus x hat, u minus u hat, where x hat and u hat are the states and actions around which we linearized. So now we're going to express our dynamics as linear in the deltas, in these differences. And the same way the cost is going to be expressed as quadratic in the deltas, in the differences between x and x hat, u and u hat. And then the matrix part is the derivative. Here the matrix is the second derivative, and the vector is the first derivative. So that's our delta x. This is our delta u. And then we're going to do LQR with the dynamics given by f bar there, the cost given by c bar, the state delta x, and the action delta u. So we'll basically compute the optimal delta u's. So the way that the iterative LQR works, here's the pseudocode. Until convergence, we're going to take our nonlinear dynamics, compute their derivative, and set that as our dynamics matrix component f. We'll take our cost, we'll compute its first derivative and its second derivative to get big C and little c at every time step. Then we're going to run the LQR backward pass on the state delta x and on the action delta u. And then, so that'll get us a controller capital F and lowercase f. And then we'll run the forward pass. And when we run the forward pass, every time that we use the dynamics in the forward pass, we'll actually use the true nonlinear dynamics. But we'll compute the action according to the same rule as in regular LQR. And then we're going to update our x hat and u hat based on the new states and actions that we saw from the forward pass. So the new x hat will become the x that we saw when we did the forward pass, and the new u hat will be the u given by this rule. So that will update our trajectory to a new trajectory. And then we go all the way around again, relinearize around the trajectory, re-expand the costs around it, perform a new backward pass, perform a new forward pass, and so on. So this is called iterative LQR. Does anybody have any questions about it? OK. So why does this algorithm work? So it turns out that iterative LQR is doing something extremely similar to Newton's method, just with dynamical systems. So to get kind of an intuitive picture of this, I won't go through the formal proof of it, but to get an intuitive picture of it, let's compare what I just described to how Newton's method would compute the minimum of some function g. So with Newton's method, you would evaluate the gradient of g. You would evaluate the Hessian. You would update x to be the thing that minimizes this quadratic function, and then you would repeat. So in iterative LQR, we did essentially the same thing. We take our current trajectory instead of our current x. We take our whole trajectory, we compute derivatives and second derivatives, and then we minimize a quadratic system, and then we update our trajectory. So iterative LQR is doing something extremely similar to Newton's method. It's locally approximating a complex nonlinear function via a Taylor expansion to get a very tractable function, optimizing that tractable function, and then repeating the whole process. In fact, so it's an approximation of Newton's method, and you can actually exactly get Newton's method out of iterative LQR with one small modification. So iterative LQR is not exactly Newton's method. The modification that you need to make it exactly Newton's method is to introduce second-order dynamics approximation. So far we only had first-order expansion of the dynamics and second-order expansion of the cost. If we also do second-order expansion of the dynamics, meaning we put in the second derivative of the dynamics, we can actually derive a slightly modified backward recursion, and that will be exactly Newton's method. So that'll just be a very peculiar dynamic programming approach to applying Newton's method to trajectories. Now, in practice, we often don't use the second derivative of the dynamics because this thing is a much larger object because the dynamics are vector valued, so you actually end up with a tensor, and it gets kind of messy. And in practice, actually, the first order dynamics works pretty well. It takes more iterations to converge, but compared to the computational cost of computing those second derivatives, it's often worth the additional iterations. But the full algorithm where you do use the second derivatives, this is what's called differential dynamic programming, or DDP. So if you see DDP or iterative LQR is just DDP without the second derivative terms. Now, there's a little bit of an issue that I haven't covered yet that it's kind of important to get these methods to work well. And to understand that issue, let's go back to regular good old-fashioned Newton's method. So if you do regular good old-fashioned Newton's method, and you update your x by exactly solving this quadratic, this is often not actually a very good way to do Newton's method. Does anybody have any idea why this might be a bad idea? If you're doing Newton's method, why might you not want to exactly solve that quadratic problem?
Because the h and the g are, the h is local in x.
Right, so the g and h are a quadratic approximation to some complicated nonlinear function, but it's a local quadratic approximation. The actual function is not actually quadratic. So the local function might be some horrible monster like this, and you're sitting at some point on these hills, and you're drawing a parabola. And then you're saying, well, let's just go to the bottom of this parabola. But when you actually go to the bottom of this parabola, you might go pretty far from where you started. And at that point, this quadratic fit to your function might have been pretty bad, and you might have actually gotten worse than where you were when you started. So for this reason, if we actually do Newton's method for optimization, typically, we would want to do some sort of line search. We'd want to backtrack a little bit and find a place where we do actually get improvement. And in fact, for iterative LQR or DDP, we want to do basically the same thing. So for iterative LQR, this is the pseudocode that I showed you before. And the part where you introduce this line search is actually right here when you run the forward pass. So when you run the forward pass, what we can do is we can take this lowercase k, and we can multiply by a little constant. And the thing to note about this little constant is that if you set alpha to 0, you actually don't change your trajectory. Because if alpha is 0, then the first state matches the first state, so this term is 0, and you just take the old action. When you take the old action, the second state also matches the second state, so this term is 0 for the second state as well, and then you take the old action. So this lowercase k term is the only thing that actually changes your trajectory in the forward pass. So if you put a little multiplier on that, and you walk that multiplier back from 1 all the way back to 0, you can interpolate between the old trajectory and the new one. So you can do your line search on alpha, and that will let you actually search between the updated trajectory and the previous trajectory. The kind of line search that you can use is up to you. So all the usual literature on line search is applicable there. But if you're in a hurry and you want to implement something simple, just cut it in half every time and do it that way. In practice, one of the things that's really useful to do is to have some sort of optimality condition. So you don't want to necessarily reduce your step size until you get some amount of improvement. What you want to do is you want to compute how much improvement you expect, and then walk it back until you get some fraction of the expected improvement. Because sometimes it's better to walk it back even further. Like if you imagine this thing backtracking, you don't want to stop it right when it hits the same height on the other side. You want to actually walk it back until it gets to the optimum. OK, so you search over alpha until improvement is achieved. A little bit of additional reading on these kinds of methods. This is the Jacobson and Main monograph on differential dynamic programming. So this is actually the the work that originally introduced DDP. So if you want to read some classical literature on optimal control, that's actually a good reference for that. This is a much more accessible kind of recent paper. It's not actually the paper that introduced iterative LQR, but it does provide a relatively readable and accessible description of it. So if you want kind of a primer on iterative LQR that goes into a little bit more detail in today's lecture, check out that paper by Tasa, Ares, and Todorov. This is a paper that I'll discuss a little bit in a subsequent lecture that actually looks at a different way of doing line searches. So instead of doing a line search on alpha, it actually does a trust region on the distribution of trajectories. And I'll discuss it a little bit more in a subsequent lecture. So if you want to learn about a different way to do the line search, that would be a paper to check out. And to wrap up, I want to show you a little video of this iterative LQR method in action. So for this work that I'll show you, this is not a deep reinforcement learning paper, but it does demonstrate some really interesting results just using this iterative LQR algorithm. And the only additional kind of magic here is that beyond using iterative LQR, they do what's called model predictive control, which means that they replan every time step using iterative LQR. So the whole controller that they're going to demonstrate basically works like this. You observe some state in a particular time step. You use iterative LQR to construct a plan for some time horizon that minimizes the cost. And then you execute the first action along that plan, discard the rest of the plan, and then observe the next state. And this is called model predictive control, and we'll talk about that a little bit more next week. And here are some of the results that they get. It's actually very interesting to watch. So these results, there's nothing that's actually being learned. Everything is being synthesized online, basically in real time. So here, they apply a little perturbation force to these little characters, and they're trying to achieve some goal, typically standing up. So this is a kind of a classical benchmark system, a relatively simple system. And here, they turn on the controller, and the controller is trying to figure out how to swing upwards and stand upright just by actuating the elbow joint. So it's an under-actuated system, sort of like a gymnast. So here, it figures out very quickly how to get itself to stand up. And then they turn off the controller, it drops, wobbles around a bit, and then they turn it on, and it can recover. So this is a relatively low-dimensional system. It figures out how to stabilize itself in the presence of perturbation forces and so on. This is a more complex system, so this is a multi-jointed swimming snake. And here it's trying to avoid the red thing and get to the green thing, and you can see that essentially in real time it kind of discovers this gate, and this is all using iterative LQR, replanning every time step. It assumes a known model, so it's actually using the real model, that simulator, to do the planning, but other than that, it's all online. And there it goes. So it actually just figures out this little steady state swimming gate on its own. This is a little hopping robot, so it's a little planar monopod. It's constrained to be in 2D, and they just drop it on the ground. They apply some forces to torture it a little bit, and then at some point they're going to turn on the controller to try to get it to stand up. So now the controller is on, and it figures out how to stand itself up, and then they're going to push it a little bit, and when the controller sees the perturbation, it tries to recover. Here, what they're doing is they're lying to the algorithm. They're telling it, this thing is actually heavier than it really is, so the planning is done with the wrong model, where in the real world, the mass is half of what the model thinks it is. And here, the mass in the real world is double what the model thinks it is. So now, in the presence of model errors, you don't get optimal plans, but because you're replanning every step, you can essentially treat the model errors as perturbations and compensate for them to some degree. Here's a more complex system. This is a 3D humanoid. And when they let it go, it just kind of falls. I'm not sure why they need to torture it at this point, but when they turn on the controller, it figures out how to stand up and stay standing up even in the presence of some perturbations. And then they turn off the controller. So the nice thing, if you have the true model of the system, and you can actually plan through that model effectively, the nice thing is that you can get really complex behaviors that essentially emerge instantaneously. So here, this system didn't actually need to see situations like that in advance. It's just using the model to figure out how to react appropriately, and things like using the hands to brace against the ground when it falls essentially emerge organically, automatically. So the main point I wanted to make with this video is that if we do have good models, there's actually some pretty impressive things that we can achieve essentially with no training. So this is maybe a little bit of motivation to think about how we can acquire good models of systems even when that have unknown dynamics, so that we can do stuff like this in real time online without having to worry about long training periods and without having to worry about the system seeing something new that it was unseen during the training. All right, and there it's waving goodbye to us. Yes?
So with the iterative LQR, you basically need to choose some initial guessing, right? So what would be the initial guess?
Yeah, so the question was, with iterative LQR, you have to choose some initial guess around which to linearize. If you're doing model predictive control, like these guys are doing in that paper, a very good initial guess is actually the last trajectory that you computed. So if at the previous time step you computed some decent trajectory, at the next time step you can just initialize with that and put a random action at the very end. If you don't have a previous time step, then you either use some prior knowledge or you initialize with something random. All right, so we talked about what we can do with known dynamics. Now, what's wrong with known dynamics? Well, in some cases, nothing is wrong. So if you're driving your car and you have a very good kinematic model of your car, maybe that's perfectly fine. You should use your known dynamics. But there are things in the real world that defy our ability to write down very accurate analytic models. So if you have things that range from very physical to more abstract, if you have a robot manipulating some cloth, for example, well, maybe that's a really hard situation where you can't just write down a set of equations that perfectly model that cloth. If you have a system that's interacting with humans over the internet, for example, well, maybe describing the dynamics of that interaction is just fiendishly complex. And the best that we can hope for is to be able to somehow model them from data, because the kind of equations that we can write down will be hopelessly wrong. So that's the kind of stuff that we'll talk about next week when we start getting into model-based RL algorithms. All right, see you then.
For the LQR with dynamic systems, and if it's a linear system, and whole trajectory. But then you execute the first action, you see the second stage, you